During nuclear fission of a uranium-235 nucleus, 2 to 3 neutrons are released. If at least one of these neutrons strikes another uranium-235 nucleus and causes it to fission, then a chain reaction will occur. The chain reaction may be made to proceed in a controlled manner, such as in a nuclear reactor, or explosively, such as in an atomic bomb. If exactly one neutron from each fission induces fission of another nucleus, then fission will continue at a constant rate. This kind of chain reaction is called a critical chain reaction. Click the Criticality button. If more than one neutron from each fission induce a further fission, then the chain reaction grows. The rate of reaction increases until finally the rate of energy released is so great that an explosion will occur. This kind of reaction is called supercritical chain reaction. Click the Supercriticality button. Sometimes none of the ejected neutrons will induce further fission. Then the rate of reaction will slow down and reaction finally stops. This happens in a subcritical chain reaction. The energy released in the nuclear chain reaction is enormous, far greater than that in any chemical reaction. By comparison, the energy produced in a nuclear fission can be about 20 million times greater than in any chemical reaction. The possibility of producing large amounts of energy from nuclear fission led to the construction of the world's first nuclear reactor in Chicago in 1942. Since then, many commercial nuclear power stations have been built around the world. The diagram above is a model of a pressurized water reactor. The nuclear fuel consists of enriched uranium rods which are surrounded by water that acts as the moderator. Fast-moving neutrons ejected by uranium-235 fission are not readily absorbed by other uranium-235 nuclei to cause additional fissions. They have to be slowed down from about 10 to the power of 6 meters per second to 10 to the power of 4 meters per second by graphite or heavy water which acts as a moderator. At this speed, they are known as thermal neutrons, as their speed depends on the temperature of the surrounding material. Boron-coated steel rods are used as control rods to absorb neutrons and thus control the rate of fission. Lowering the rods into the reactor core will slow down the reaction and lifting them will speed up the reaction. When there is a dangerous increase in core temperature, they can be dropped into the reactor and shut down the reactor. Drag the control rods to lower or raise them. Energy is transferred from the reactor to a boiler where water changes into superheated steam, which is used to drive turbines, just as in a conventional power station. Summary: a chain reaction will occur if at least one neutron strikes another uranium-235 nucleus. In a nuclear reactor, high-speed neutrons are slowed down by a moderator to produce thermal neutrons. The control rods control the rate of fission by absorbing neutrons. For several billion years, the Sun has been radiating energy at the rate of 3.9 times 10 to the power 26 watts. This energy, which allows life to exist on Earth, comes from thermonuclear fusion. As mentioned earlier, a temperature environment of several million kelvins is needed for fusion to take place. The condition in the Sun and other stars is just right for this process to occur. The fusion reaction in the Sun is a multi-step process in which hydrogen is burned into helium. The process by which this occurs is called proton-proton or pp cycle. Click the Step 1 button. The pp cycle starts with the collision of two protons to form a deuteron. Simultaneously, a positron and a neutrino are created. Click the Step 2 button. The deuteron collides with another proton to form a helium-3 nucleus with the emission of a gamma ray. Click the Step 3 button. Two helium-3 nuclei collide to form an alpha particle and two protons. Hydrogen burning in the Sun's core has been going on for about 5 billion years. Calculation shows that there is enough hydrogen left in the Sun to keep it going for about the same length of time into the future. What will happen then? Answer. The Sun will start to collapse under its own gravity. This will raise the core temperature and cause the outer part to expand, turning the Sun into what is called a red giant. It is difficult to initiate fusion because of the electrical repulsion between protons and an extremely high temperature is required. At such high temperature, matter is in the plasma state. The main problem is the confinement of the plasma. At such a high temperature, holding the plasma in a stable arrangement and allowing fusion to take place is very difficult. The best solution so far is to use a magnetic field to confine the plasma's charged particles in a ring. The model above shows a tokamak, an evacuated donut-shaped chamber which uses magnetic force to confine the plasma, preventing it from touching the walls of the chamber. Summary. Thermonuclear fusion takes place naturally in the Sun. The fusion reaction in the Sun is a multi-step process called proton-proton or pp cycle in which hydrogen is burned into helium. Fusion of nuclei can only take place at extremely high temperatures at which matter is in the plasma state. In a fusion reactor, a magnetic field is used to confine the plasma.